Okay, welcome to this first Prelab. I'm going to try this for this new year to have these Prelab assignments, which will be something to listen to or to read before a lab so that when you come into lab, you're ready to go and a lot of the preliminary stuff has been taken care of. So this is going to be about the language Prolog, which stands for programming logic or programming with logic or something like that. And this goes back to the early 70s and is very popular with a lot of logicians and artificial intelligence people and mathematicians because there's actually some really cool things you can do with Prolog. We're only going to scratch the surface of the language, but that'll be enough. So first of all, for running this, we're either going to use the VNC to connect to Euclid, or I'm going to try to get a Windows Prolog client that you can go ahead and use. If you have a Mac, you can actually install gprolog on your Mac. And I'll have more details on this as I figure out what the easiest thing to do is going to be. So some notes on using Prolog. This is an interpreted language. This means that there is literally an interpreter prompt, and you can type stuff directly into it, and it will either add that fact to its rule database, or it will try to respond if you phrase it like a query. We'll see how to do that. You can also put your files, your programs, into a file with a .pl extension. For people who've done Perl before, this might look confusing because PL is often used for Perl. I assure you in this case it's going to mean Prolog. So for example, you would have myprogram.pl. You can load programs from the interpreter prompt by doing square bracket myprogram, close square bracket, and then a period. Periods are very important in Prolog. That's your end of line character rather than semicolons like in languages you might be used to. Note that for this to work, you have to actually be running gprolog from the same folder where you're putting these .pl files. Otherwise, when it tries to load it, it won't be able to find it. And note that if you make changes to your file, it does not automatically reload them into the rule database. You actually have to sort of retype this or use the up arrow to get to it. Here's a link to some more information about the Prolog language. It's sort of a wiki of sorts. It's actually kind of interesting. So Prolog, this is sort of really a different paradigm than what we've seen before. You're going to define rules and patterns and then ask Prolog questions about them. It will then use logic, first-order logic specifically, to go through and try to answer them. There's a specific algorithm called resolution, sometimes called unification. Either that or it's related to unification. I can't quite remember. But resolution and horn clauses are the two things you'd want to look at. It's a way of formally converting a bunch of things to logical clauses and then trying to go through and figure out what you can prove is true. So Prolog has predicates, atoms, and variables. You might recognize those terms from first-order logic. We're definitely getting this from first-order logic. The predicates, these are like functions. They have to start with the lowercase letter, and they can have 0 or more arguments. Atoms, these are concrete parameters that would plug in to a predicate. These start with lowercase letters, and they're like atoms from first-order logic. And then variables, these are unknowns. They have to start with an uppercase letter, and these are like variables from first-order logic. In fact, we chose to use the terms predicates, atoms, and variables, and have the conventions of lowercase letters for atoms and predicates and uppercase letters for variables because we'd be moving into Prolog. So here's an example. You would type into your interpreter, for example, woman Alice, man Bob, and siblings Alice Bob. This means that Alice is a woman, Bob is a man, and they're siblings. We could then ask Prolog questions. So if we ask if Alice is a woman, Prolog would come back and say yes. If we ask Prolog woman X, where X is a variable, we're saying, well, what are all the women you know about? It'll come back and say X equal Alice. If we say, well, what are all of Alice's siblings? So siblings Alice X, it'll come back and say, well, X is Bob. So some notes about this. Well, first I want to actually try this out. This is my first attempt at a live demo here. Oh, you can't see this, but the screen recording thing is in the way. There we go. So on my Mac, I'm going to type well, let me check where I am first. Oh, that's not where I want to be at all. Knox 262 Prolog. Good. Okay. Crap. I didn't think this out very well. I need another window. Okay, so now I've got two windows. Oh my god, really? You're going to take that long now that I'm recording? Ugh, there we go. Okay, good. Knox 262 Prolog. So we're going to come up with example1.pl. We're going to put into here woman Alice, man Bob, siblings Alice, Bob. Great. Now we're going to flip back to this window. We're going to run gprolog in that same folder. And we're going to say, okay, go ahead and load, what the hell did I name that again? Example 1. Oops. Example 1. And it's going to come back and say, hey, look at that. I managed to load all of that. Now we can start asking questions. Okay. Is Alice a woman? It'll come back and say yes. Oops. Is Alice a man? No. Is Bob a man? It'll say yes. Watch this. If we ask if Steve is a man, it'll come back and say no. Not because Steve isn't typically a man's name, but because we haven't told this particular set of rules anything about Steven, so it's going to come back and say no. It certainly can't prove that. And then if we say, well, oops, you know, man X, is going to come back and say, well, X equals Bob. And when it says yes, that means that's all it's able to find. So that's just sort of a simple example. That's the interactive nature. One note, it drives me crazy when people just keep sort of retyping things. On any reasonable shell on one of the Macs, or if you're using the VNC, you can use the up arrow, as I'm doing right now, to scroll back through all these previous commands. So suppose we go back here to example 1. Maybe we've made some edits. Maybe we've added something else here. Maybe we now know that Steve is a man, and we've gone ahead and saved this file. We go back here and reload it. Oops. Now we can ask, who are all the men? It'll come back with Bob. If we hit the semicolon, it'll then come back with Steve, and it's going to keep doing that. And when it runs out of things, it can't prove any more people are men. It'll just come back and say yes, meaning it's done, and it found at least one that seemed to fit. So that's kind of what's going on there. I'm going to jump back to Firefox and keep going because I'm already 8 minutes in. So you can also define rules or predicates using variables. So this is kind of taking our same example. We've got Alice a woman, Bob's a man, Alice and Bob are siblings. We could say brother X, Y, if X is a man and X and Y are siblings. So this means essentially that X is a brother of Y if X is a man and they're siblings. Now, for the brother predicate to be fulfilled, we have to be able to fulfill all parts of the right-hand side with essentially a rule that involves a predicate and only atoms. So we're hoping to sort of take stuff like this and start plugging it in over here and see if this ends up being true. So how does Prolog try to answer these questions? Well, I mean, it's going to sort of look through its set of rules. It's predicates that have atoms. These are sometimes called facts, to see if any of the facts fit the pattern. Then it's going to try to fulfill any rules by replacing rules with other rules, which may themselves be rules that require more substitution with other rules and so on. You can kind of see we're heading towards recursion here. So it's basically lots of recursion. If we sort of have this in here, and we ask, well, who is Bob the brother of? It's going to sort of take this brother rule, and it's going to use this to expand it out, where Bob is bound to X. It's going to sort of plug those things in, and then it's going to start looking through all the siblings rules to see if it can fulfill that. For this particular rule database, it can, and it's going to come back and tell us down here that X is Alice. Now, if the siblings rule were defined in terms of other rules, or if there were other siblings relationships, it's just going to keep plugging these in and try all of them. So you can sort of see that this is, potentially exponential in the worst case. So this brings up the question, does this always terminate? No, there's some queries Prolog can't answer, or at least that it can't answer quickly enough. You're highly unlikely for this assignment to come up with a rule database that's that complicated, but it is possible, and it's an interesting thing to kind of think about. If all of these things in logic end up being, in the worst case, exponential, how is Prolog going to handle this? In practice, and this is well beyond the scope of this course, but just in case you're wondering, in practice, there's a special command called cut, which basically means, if you've searched this far and haven't figured it out, cut. Don't look any further, just return a no. And in this case, no doesn't necessarily mean I can prove it's false. No means I can't prove it's true. So in general, the way Prolog works, if it can prove something's true, it usually can figure out a way to do that. But if it can't show that something's true, that might mean it ran out of time or that it's false. So that's just something to keep in mind. It's not always going to be able to terminate, which is kind of unfortunate. So predicates are not reflexive. So if this is our rule database, Alice is a woman, Bob is a man, and Alice and Bob are siblings, and we ask, well, are Bob and Alice siblings? Prolog's going to say no, not because Bob and Alice aren't siblings, but because Prolog has no idea that the siblings relationship is supposed to be reflexive. So we want to think about how we might fix this. Now, before we go about fixing the siblings rule, one weird note, Prolog actually doesn't know anything about these relationships. You could say aliens, Alice, Bob, but then use it like the siblings relationship, and Prolog wouldn't really care about the difference. You could say it's the WXYZ relationship. Prolog really doesn't care what you name these predicates as long as they start with the lowercase letter. You could name it the foo relationship. It really has absolutely no idea, because Prolog is actually very dumb. So how would we make this reflexive? Here's a way not to do it. So siblings XY is true if siblings YX is true. Why is this a bad idea? Well, this leads to an infinite recursion. Because remember, we already know that Prolog tries to solve things by repeatedly plugging in different rules. So that's just what it's going to do. It's going to say, well, siblings XY if siblings YX. So let's go ahead and plug that in. Well, siblings YX if siblings XY, and it's just going to keep plugging these in infinitely, and then it's going to run out of memory and crash. And that's not really what you want to do. So the sort of less elegant looking, but far more effective in practice way is, if you want something to be reflexive, easiest thing to do is just define it both ways. So this way we know that, in fact, if Alice is Bob's sibling, then Bob is also Alice's sibling. So another thing is, you may have multiple facts. So you may have multiple men, multiple women, Alice, Bob, Charlie, and Della. And if you want to do that, you have to group all the like predicates together. So, because believe it or not, having these on separate lines, implicitly they're all joined by ors. So you want to have all your man predicates together, all your woman predicates together, and so on. If you do it like this, you intersperse them, you're going to get an error saying something like discontiguous predicate, man 1. This means the man predicate that takes one argument or one parameter is discontiguous because it's got something else in between it, and Prolog doesn't really allow that. It doesn't allow that at all. Another note is about equal and not equal. Prolog and SQL, or SQL, another language we're going to learn later in this term. These are two of the few languages I'm aware of where equal, a single equal sign, actually means equals. You can use it the way mathematicians would. In Prolog, slash equals means not equal, kind of like the bang equal or exclamation equal in many other languages. And for assignment in Prolog, we actually just literally use the word is, as in x is 3. So, you can sort of tell that this is a language that comes out of a mathematical and a logical tradition rather than a more traditional sort of computer science-y engineering tradition. So examples of using equal and not equal, so we could define an equivalent relationship of x, y, and define that if x equals y, like using this equal sign, and same with different x, y, we could say, well, if x not equal y. And this is actually totally going to work. We can actually plug in any atoms we want, into this equivalent. We could say equivalent Bob, comma Bob, and Prolog will come back and say yes, because Bob in fact equals Bob. It's going to plug these in and see that they're in fact the same atom. Similarly down here. So that's not terribly useful because you don't need this predicate or this predicate because you already have these built-in primitives. Here's a situation where it is useful. So suppose you have this professor relationship. So we know that Spacko is the professor of Sam, and Spacko's also the professor of Josh. Oh, crap. I made an error here. Pretend these two teachers say professor. I don't really feel like re-recording this because it's already after midnight, and I got to teach FP at 8 a.m. So pretend that this says professor, and pretend these two teachers also say professor. So if we want classmates, X, Y, are people in the same class, well, if there's some Z that's X's professor, and some Z that's Y's professor, and X does not equal Y. X does not equal Y is very important. Otherwise, this would happily tell you that Sam is Sam's classmate, and Josh is Josh's classmate, which is not true. Sam is not in the same class as Sam. Sam is Sam. So without this, that's a situation we have to put this X does not equal Y in there. God, I have to remember to go back and fix that. That's right. That's going to drive me crazy about the professor and the teacher thing. I originally had it written with teacher, and then I changed it to professor, but I didn't change it ever because I thought it made me sound more distinguished, since, I don't know if you can guess, I'm the Spacko in this example. So another example of something cool you can do with Prolog with recursion, we talked about this in the first-order predicate logic stuff. We have this above relationship. X is above Y if X is on top of Y. And then X is above Y if X is on top of some Z, and Z is above Y. Now this implies that somewhere in our rule database on top, this is sort of the relationship directly on top, we're going to have some facts, in other words, some predicates that don't rely on variables that actually have atoms plugged in there. So we've got on top Cubs Yankees, because the Cubs are better than the Yankees, and then on top Red Sox Cubs, because, I kind of like the Red Sox more than the Cubs, and I'm writing the example so I can define the rules any way I want. So then if we ask above Red Sox Yankees, Prolog's going to come back and say yes, because it's going to sort of do this recursively. First it's going to see that the Red Sox are on top of the Cubs, then it's going to define this above rule by plugging another on top in there, and then another on top at the end. The final above will sort of be defined by this base case, this first one. So this is sort of a really cool example of recursion. It gives us a really elegant way to define things. Now, a warning about doing recursion. You put your recursive rule to the right, not the left. In other words, the base case goes in the left, the recursive rule goes in the right. The reason for this is Prolog actually plugs everything in from left to right. So if you define it this way, above with above and then on top, it's going to keep trying to plug stuff into this above, basically this rule forever, and eventually run out of memory and crash. Whereas if you do it this way, since it has to fulfill these rules from left to right, it's going to try to use the facts first, and the facts are kind of like the base case. This will never terminate unless it can plug in a whole bunch of aboves. So the recursive rule always put the base case on the left, the recursive call on the right. Prolog can actually do other kinds of recursion. If you want to do factorial n and result, we can define this as well. N less than or equal to 1, result is 1. This is kind of an assignment. And then factorial n result, well, if n is greater than 1, we're going to define this variable n minus 1 is literally n minus 1, and then we're going to do factorial n minus 1 temp. This looks like a recursive call, but it's actually not, and then result is temp times n period. And so if we plug in factorial 5 comma x, we'll get back x equals 120. There's no real return values in Prolog. We sort of have these extra result parameters getting passed into these predicates. We're not going to do any actual computation with Prolog. We're just going to define rules. We're actually going to do a family tree with, brother and cousin and siblings and uncles and great-grandparents and all these other different types of rules. So we're not really going to do any computation, but it can be done with Prolog. It is a Turing complete language, so you can kind of do cool stuff like this. We're just not going to. So some other notes, you can't inline computation. You couldn't say factorial n-1 temp. You have to actually define a variable and then sort of do the recursive call, because it's not really a recursive call. What you're actually doing is like defining bits of logic that have to be fulfilled, and there's no real return values. We plug in these, these other variables to these predicates that just kind of hang around and pick up these values. And also, Prolog is first order. So you can do this, brother xy, if x is a man and x and y are siblings, but you can't do this, commutative xab, if x of ab is equal to x of ba. This isn't going to work for that first order restriction that we saw. Predicates can range over atoms, but a predicate can't have a variable which then gets used as a predicate in the list of things that need to be fulfilled. That doesn't work. That would be a higher order logic. That would not be first order logic, and that doesn't work for the same reason we saw that first order logic doesn't allow quantifiers to range over predicates themselves. It only lets quantifiers range over variables. Now, of course, there's extensions to Prolog to try to make it higher order, but you start running into even more undecidability issues when you start dealing with higher order logics. I think that's everything I've got. Oh, what sorts of things are like Prolog? In other words, what problems lend themselves to Prologian solutions? Automated theorem provers in mathematics are an obvious choice. Different types of expert systems. Believe it or not, lots of GRE logic problems lend themselves to Prolog. Also, constraint solvers, or at least sort of constraint solvers. So if you want to figure out how to schedule C courses into R rooms at T times on D days with that faculty so that there's not a certain number of conflicts, you could use Prolog. You could also use something like a constraint solver, of which there's a number of them out there that you could try out. But they use a lot of the same sorts of logic that Prolog's going to use. So that's what I've got. That should be enough to get you started on Prolog. Thanks for listening.